Okay, good afternoon, ladies and gentlemen. My name is Stefan Jankowski, so I start as a first. And I'm representing Maritime University of Szczecin, Faculty of Navigation. My main field is maritime traffic engineering, but we were asked to prepare training because we take a part with two projects, Martech LNG and Go LNG. And I'm sorry for all, because the training was prepared for wide spectrum of audience, so from students to the professionals. So I'm sorry for the points which are obvious for you. Okay, so for the last few days, 2 days, we heard about the market, about the business, about the opportunity, model business, and so on. And today, with this training, we want to approach you a little bit more the fuel itself, this LBG, liquefied biogas. So we talk about the properties, we talk about the hazards. So that part is mine. Okay, so the biogas is environmentally friendly, renewable source of energy. And it's come because all organic matter decay anyway. So producing methane, producing CO2. And by gathering these gases, we can, first of all, produce a fuel, renewable fuel, and also save our planet because of reduction greenhouse emission. And for example, in the United States, every year, 31 million of tons food waste are discarded in the landfills. So this amount of biomass producing also CH4, so methane, and CO2. Okay, so we can reduce this emission. Okay. The biogas can be used also in the circular economy. So, for example, in the landfills, in the agriculture, all organic matter when it's producing on the farm can be used as a biomass. The biomass decay, we can produce methane, which can be used to power the machinery or to heat the building. But yesterday we also heard that this is not the most efficient way for using it. So the best is to make a pure, because as we see on the next slides, the compositions of the biogas, the raw gas, is quite low with methane. So we can remove all impurities and then make almost pure methane. So, simply says, we have to produce biogas, we have to have the source of this organic matter. We have delivered it to compartment, the closed compartment, where without oxygen and with some kind of microorganisms to speed up the process, we can decompose this biomass. And all gases which is gathered above surface are then go to the tank, and we can use it as a fuel. The rest of the biomass can be used in other way, like for example fertilizer, and we heard about this also yesterday. Biogas and biomass are both biofuels and are both renewable source of energy, but for biogas, the biomass is the raw material, and in this case, biogas is the end product. And there are few directives, European Union, which describe this biogas as a renewable source of energy. So both here, biomass and biogas are this environmentally friendly source of energy. Okay, we heard also that there are different kind of waste which can be used for for producing biogas. But we can see that about 60% of this production, the gases, when we decompose this biomass, is methane. Then about 30% is CO2, then nitrogen, some amount of oxygen, and also quite a lot of HO2, so water. And some other residuals, which is very small amounts. So that's why using locally as biogas to power the machinery and heat the houses is not so economic, because the heat power is quite lean, yes, because it's only 60% of such a of methane in this biogas. So what is the difference between biogas and natural gas? Because actually they are the same element. I mean the methane, I mean compounded element. So there is the time. So the production method, the natural gas is produced by the time when the pressure, temperature also decompose this organic matter and make methane and heavier hydrocarbons. And biogas is, as we said, is the gases which are gathered, captured from this above this biomass which is decomposed. The second difference is the quantity. So here we have the natural gas, I think, because I don't see, yes, and here we have the biogas. And this is the statistics for, let's say, 2-3 years ago. And you can see that the biogas is about maybe a little bit more than 1% of natural gas. So two main differences is the production method and quantity. Hopefully, we can also hear that the production amounts of biogas is increased year by year. So this is our hope. But because it's a quite small amount of the biogas, we can blend it with natural gas, make it more friendly. And for example, some EU directive describe the target that by 2020, 10% of energy in transport and 20% energy for producing energy should be used with this renewable source of energy. It's a mix, but also then biogas can be used to improve these indicators. Okay, so the next difference with natural gas and biogas is the composition. Because as you can see, that here we have only methane in biogas. There are two kinds of weights, so almost the same. But with natural gas, we have also the heavier hydrocarbons. And this is another advantage for biogas, because with natural gas, actually with liquid natural gas, we have the phenomena which is called aging. And aging is because the first compound which vaporizes is methane, and the composition is changing, and the heavier hydrocarbons left, so the parameters of the gas in the tank is changing. In case of biogas, we don't have the heavier hydrocarbons, so when we remove all of these impurities, we have almost pure methane. I think. Okay. Okay, the treatment process is to remove. We have to remove the water, of course, because water could make some hydrates which block the facilities, the infrastructure. We remove all acid gases, so H2S, C2O. Then we remove also the water. In the red box, we have this part which is for the natural gas, so we have to remove also these liquids. I mean the heavier hydrocarbons, and then we can the product to final compressions to achieve the liquid state of the methane. Okay, a little bit physics. So actually all compounds, all elements has three states of matter. We call them gas, we call them liquid, we call them solid, because in the room temperature and the atmospheric pressure, they have such a state of matter. But it depends on the internal heat. When we deliver a heat, we can pass from one to another state of matter. When we remove the heat, also we can pass. So here is the phase transitions. When we have a solid, when we increase the heat, internal heat, the particles start jingling more, and then we have liquid. So the process is called fusion. When we deliver more heat, more energy, then from liquid through vaporizations we can obtain a gas. In some temperature and pressure conditions, we can go directly from the solid to the gas, and it was called sublimation. And it could happen in the triple points, which will be discussed on the next slide, I think. Okay, so during the phase transition, we have some hidden latent heat, because, for example, when we have this phase, so we have solid, and this on the, on the left side we have the temperature for the water. On the right side we have temperature for the methane. So when we deliver the heat, we have increased the temperature. At 0 degrees we have the fusion, so melting, the ice is melting. And in this case, until we obtain all liquids, we deliver a heat which is called the latent heat, hidden. So after we achieve all water or liquids, then we can also warm up the liquid. And in this point and this temperature, for the water 100, for the methane minus 161.5 degrees, we have the next stop, the vaporization. So also when we deliver the heat, we do not increase the temperature, but we increase the amount of vapor. And then when we have only vapor, then we have also heat them, the gas, to the higher temperature. There are three properties which can describe the gas: so volume, temperature, and pressure. And there are three rules which describe, which govern this process. So we have the Boyle's law, which describe how the relation between the volume and pressure. Then we have Charles' laws, which describe the relations between temperature and volume, and also Guy-Lussac's laws, which describe the relations between temperature and pressure, but in the closest space. Okay, as we said, all substances or compounds has three states of matter. So here we have the typical phase transition diagram. And this blue line show us the boiling temperature in different pressure. This boiling line is limited with 2 points, the triple points, where we have actually 3 states of matter. We have a solid, we have a liquid, we have a gas. And then we have, on the other end, we have a critical point. And critical point is the highest temperature in which such a substance has liquid form, liquid state. Behind this point, even if we increase pressure, it will always be a gas. Okay? A gas, the density will be the same like the liquid, but the pressure would be much higher. So the boiling temperature for different substances or fuel is as follows. It's of course in the atmospheric pressure. So water, of course, 100 degrees. There are the others hydrocarbons. Here we have CO2, and methane is boiling in minus 161.5 temperature, degrees of Celsius. And here is the same diagram for the methane, and we can see that the triple point is at temperature somehow like 188. Then we have the critical temperature about 82 degrees, which means that if we have methane, liquid methane in the tank, in the closed space, we cannot allow it to warm up more than this minus 82 degrees, because from pressure like this, about 45 bars, after this point we have 600 bars. So it's a quite dangerous situation. And yeah, the critical temperature for other fuels are shown on this slide. So, for example, ethylene has the temperature like a little bit more than 0 degrees. Of course, here we have the pressure. So, methane, as we said, 82. Okay, for liquefactions, there are, on the previous slides was shown a few methods for liquefaction, for liquefy this biogas. There are some examples, for example, here for the unconventional gas solutions, which offer us a few types of facility. Just an example found by short browsing. So we have from 300 cubic meters per hour up to 3,000 cubic meters per hour. Here is the Wärtsilä's example, also scalable from 6 up to 50 tons per day. So there are solutions which can be used to produce locally liquid biogas. Okay, so now the biogas has different names. I mean liquefied biogas, so it's called bio-LNG, liquid biomethane, or liquid biogas. More often is used bio-LNG as a product. And of course, using this kind of fuels, we can reduce the greenhouse emissions. And this is, on this diagram, we have the comparison with the diesel. And when we take a diesel as a 100%, so in LNG, liquefied natural gas, we reduce emissions of CO2 by 20%, so it's 80% of the CO2 as is for the diesel. When we blend 17% of biogas, we reach the 63% of CO2 when we compare to diesel. When we use pure biomethane, biogas, then we can even have the negative numbers, but in conditions that we also the 30% of CO2, which is in the raw biogas, captured and used for other purposes. The other purposes can be, for example, producing synthetic methane using this CO2, for example, and hydrogen. And as a product, there is no difference in properties. So we have both LNG and bio-LNG as the same fuel, actually. And some of producers issue this safety data sheet, which is for the both such a liquid. In this case, we have gasum, I think. Okay, the characteristics of liquefied biogas, liquefied biomethane, is that we, during liquefaction, reduce the volume. In the gas status, we have 600 cubic meters. And when we compress and cool down to liquid state, we have 1 cubic meters. So we decrease the volume by 600 times. And during transport and storage, we do not increase the temperature more than minus 105 degrees Celsius. Then we have 20 bars. And the base is here, about minus 160 degrees, because this is the boiling temperature. It's almost atmospheric pressure. And another point is that when we warm up the LPG, the density of the LPG will be decreased. So here we have almost solid, minus 180 degrees, and the density is about 480 kilograms per cubic meters. In case of about minus 120 degrees of Celsius, we have less than 400 kilograms per cubic meters. And this is quite important because it could cause another phenomena like rollover. The batch difference could make such a also quite dangerous phenomena or situation. Okay, so LPG is extremely flammable. It means that even at this temperature, there is amount of vapor which can be ignited. But also, it's not means that we have enough vapor to sustain this fire. Okay, it could flame for 5 seconds, but then disappeared because there is no methane in the gas state enough for sustain the fire. In order to burn, must be vaporized, mixed with air, with enough amount of oxygen. So there is very narrow proportions with air, and then ignited. The vapors itself is not explosives, but there is also some phenomena which called bliff. When we have closed space and we reach with this temperature more than 82 degrees, minus 82 degrees, then we have, as we said, immediate increase the pressure from about 50 bars up to 600 bars. And we have also, in case of maritime transport, the gas carrier, we describe this liquefied methane as a low flash point fuel, which is in the SOLAS one of the most important convention, is defined as a all fuel which has flash point lower than 60 degrees of Celsius. And okay, vapors are not explosives. Even if we ignite it, the flame is called lazy flame, so it's not explosives. Cold vapor up to minus 105 degrees is heavier than air, so will be on the bottom. So this is also quite a dangerous situation. When it warm up more than this temperature, it can be afloat up and dissipate with air. Okay, the flammability limit is quite narrow, from 5 degrees up to 15% in air. So below we have too lean, so will not burn because it's too low, too small amount of the fuel, of the methane. Above 15% we have too rich mixture, so too small amount of oxygen to keep a fire. The other fuels limits flammable range is on this table. So for example, hydrogen has the widest range of flammable, so from 4% up to 75%. In case of methane, as we say, 5% up to 15% of fuel in the air. Auto-ignition temperature. If we warm up the gas up to 537 degrees of Celsius, it could fire itself. But the high temperature is also caused that it cannot be used, for example, for the engine, diesel engines instead of diesel, because the temperature is too high. The other fuels, like diesel oil, the range is from 260 up to 371 Celsius, and gasoline also, the range is lower than in case of methane. And energy units, traditionally we describe the energy which is in the fuel with joule or BTU, British Thermal Unit, which is defined like below. We have other BTU units with MBTU, it's 1000 BTU, BTU means million BTU. Also another equivalent is ton of oil equivalent. So for the diesel is about 42 gigajoule, this 1 ton of oil equivalent. So energy density is as follows. So we have a diesel, it's about almost 40 gigajoule per cubic meter. In case of bio-LNG also, LNG is almost a little bit more than half of it. And the density of other form of natural gas, biomethane, which could be compressed, it's 9 gigajoule per cubic meters. In case of natural gas, we have at atmospheric pressure, so 1 cubic meters has only, I don't see, 0.3, I think, something gigajoule per cubic meter. Okay, the next point of this presentation is concern hazards of this fuel, and when compared with other fuels, of course, we have an energy. The fuel is flammable, so can cause a fire. In this case, we have also extremely low temperature. So all these hazards, we can divide it into two main groups for the personal injuries, so cold burns, asphyxia, and also for the infrastructure, so material cracking when we have a contact with big enough amounts of this liquid, the cryo liquid, we can make the steel very fragile and other also materials. The other hazard is bleed. I mentioned about this. So boiling, liquid, expanding, vapor, explosion is not explosion because the mixture was ignite and we have a flame, but it's because the temperature increase in the closed space and we have so pressure that the compartment would be broken and we have an explosion. So the health hazards is the burns, because it's a fire, frostbite, because of cold, and asphyxiants because low amount of oxygen. As we said, when the vapor is cold, so below 105 degrees of Celsius, it's heavier than air and push out the air from the place where we normally live, so there is no oxygen to breathe. Other risks are described on the left side this table, and we have also what should be done in case of such a situation, and we have described it also in this data sheet was mentioned before. I think Marcin will explain a little bit more about this. And environmental hazard, bio-LNG rapid evaporation is expected from both land and water with no residues left behind. So when we spill LNG or LBG on the water or on the land, it vaporized very immediately. There is no rest on these surfaces. We cannot say that it's purely environmental friendly because methane is about 20 times stronger greenhouse gas. So, of course, have an impact on the warming climate effect. And but we can say it's not significant air pollutant. We don't have emissions like burning diesel or other fossil fuel. So you can say that even LNG and LBG itself is environmental friendly, but even LNG is quite environmental friendly because it's the cleanest. It's not. It still is fossil fuel, but it's the cleanest fuel from this group. When we spill on the water, it's vaporized also immediately. Do not harm any creatures below the water surface, and do not react with water. Do not make any substances. Sometimes it's danger when it's contact with chlorine. Reactivity with other substances, so with water. Of course, when we have at the same place, I mean, for example, in the pipe, some amount of water and liquid methane, of course, the water will be as a ice, could block some pipes, valves, and so on. sometimes can create the hydrates. It's substances which looks similar to ice, but it's heavier than water, so wood can be below the surface. With air, of course, create a flammable mixture if there is enough amount of fuel and oxygen. So every time when we make some operations with tanks, we have to separate the methane with inert gas, for example, nitrogen. With other materials and with other cargo, we have always consider and consult with these data sheets, these two materials, two cargos, because we have to know if they are react with each other or not. So the same situations. And for example, for the gas carriers, always have to be considered the descriptions of the other materials, other cargo, what we should do. And ignition, explosion, flammability, hazard. So auto-ignition is quite high temperature, but anyway, when the mixture, the flammable mixture, touch the surface which is high, so it's, for example, the temperature of this metal surface is higher than 500 degrees of Celsius, it could happen the fire. The flash point of a liquid is the lowest temperature at which the liquid will involve sufficient vapor to form flammable mixture with air. So flash point is the temperature in which we can make a fire, but not sustain fire. So for example, for a few seconds. Flammability, of course, the range of fuel and oxygen, or an air, which create a flammable mixture. So, when LNG, LBG, or bio-LNG is exposed to air, it evaporates extremely rapidly, and we have, in very short time, we have explosive flammable mixture. And when we ignite this mixture, and if we have a pool of LNG, bio-LNG, we will have quite long period when the fire continue. And depends on the amount of bio-LNG, LNG, the flame could reach 150 meters high. We can see this flame, so it's visible. So about the flammability ranges we were talking already. So yeah, here is the diagram of interaction between the fuel, methane, oxygen, and inert gas, or nitrogen if you are talking about air. So this is the area in which we have flammable mixture in different proportion of these three elements, compounds. This red line is the composition in which all fuel and all oxygen is used to producing flame. So more or less is 1 to 2, so 33% of oxygen, 2 particles of methane. And here we have the line which describes the proportion with air, and here we have also this lower explosive or flammable limit and upper flammable limit. And this line also shows us the minimum amount of fuel, methane, which can produce the flammable mixture with air. Okay, as we said, we have the mixture, the vapor and oxygen or air, and if there is no ignition, there would be no fire, and we can expect that this all methane dissipate and afloat in a higher layer of atmosphere. But when during the vaporizing, during the time when the mixture is flammable and it meets this ignition source, we can have a fire. So, of course, naked light, smoking, spontaneous ignition, waste, somehow going hot and hotter, and hot work, cold work during any spark when we hit with something. Safety tools, aluminum sometimes can also, like leather, aluminum leather can cause the spark. Portable electrical equipment, and so on and so on. All this can ignite this flammable mixture. Also, electrostatic can cause the fire, and we have to avoid situation which can cause such a electrostatic discharges. So, for example, we cannot use CO2 directly to the pool of or to the vapor of methane, because as we said, when we have the pool of methane, the liquid methane, the vapor when is quite low above the surface, the temperature is about minus or less than minus 105 degrees of Celsius, and CO2 has the frozen temperature about minus 70 degrees, which means that when we put the CO2 in a gaseous state directly into this vapor, it could make an ice, and CO2 ice, of course, which due frictions can cause this also ignition. And also steam, metal reinforcements, and so on and so on. We have to follow these rules to avoid these electrostatic discharges. Toxicity hazards, there is no, the methane is not poisons. So the main problem is because push out the oxygen with air. So we can experience asphyxiation. Natomiast, so this is the limit of breathable air. So below this amount of methane particle, so 10,500 parts per million. And sometimes we can smell this the natural gas in our house because the operator adds some other substances like THT, which is extremely toxic. Of course, in proper amount. Okay, so when we have a pool, so spill with LNG, LBG, we will have some amount of liquid methane. Depends on the wind directions. We have the cloud. At the beginning, very close to the spill, we have overrich mixture. Then we have, of course, flammable, so the range is from 5 to 15% of the methane. And then we have also too lean mixture to be fired. So what's happened when we try to ignite this methane? When the cloud meets some ignition source here, the flames start and will go to this area and will flame, burn, and producing heat. The heat will produce more vapor, so the fire will also increase. When the ignition source will be somewhere here at the beginning, so the fire first go to the front of this cloud and then be at the same place like in the first example. Okay. If there is no immediate ignitions of an bio-LNG, a vapor cloud may form. There is, first of all, the lack of oxygen, so there is no breathable atmosphere. When spill occur in an open space, the liquid will rapidly evaporate to produce a vapor cloud, which will gradually disperse with downwind. And the vapor cloud or plume is flammable only over part of its area. So this is what was said before. The vapor cloud is long, thin, cigar-shaped. That depends on the speed of the wind and also the ambient temperature. So the speed of the warming up this methane and so on. So the cold vapor is denser than air at the temperature below minus 105 degrees. So initially we'll keep the ground. And the major danger from this vapor cloud occurs when it's ignited. Then we have, simply said, the fire. And the fire, of course, produces more vapor, which can sustain the fire, and the fire will become greater. But how to behave with such a fire will be told by, will tell Marcin later on. Extremely low temperature, so there is cryogenic liquids. So all substances which are not methane at this temperature can form an ice, for example, moisture. So simply says water, and there is quite danger because we can break down the facility, the infrastructure. Of course, we mentioned also that when we pour directly into steel, there will be a thermal shock. So we drop the temperature of such a substance, of such a infrastructure from, let's say, 20 degrees of Celsius rapidly to minus 160 degrees. There is no material which can be proof with such an experiment. So we will have brittle. The steel will become fragile and broken and untied. So everywhere when we expect some drops of liquid methane, we should protect it. For example, putting some tray below these valves, mostly with water, because when the drop is the drop of methane, liquid methane, touch the water, vaporize, but also condensate the water in the air, and we will see the cloud. And the cloud is not, of course, because of methane, but because of condensate moisture which is in air. Pressure hazards. To minimize danger of damage of the system, we should keep the tanks and also the pipes within this range of safety described by the producer. We should avoid opening very fast valves because we could cause this hammer shock pressure. And we should provide an instrument or facility which release the vapor from the tank if the pressure is too high. Okay, and we told also about this different density of the biomethane, liquid biomethane. And here we have some example because, of course, here we have the liquefied biogas, and this is sometimes even more amounts, percentage of methane. And where is it? This column. Here we have this. Okay, here. The last column shows us the density. So we can see that depends on the source. Here, natural gas, but also LPG. When we, for example, want to blend to make more friendly natural gas, we can achieve a quite dangerous situation when we have this batch difference. When we have one cargo, for example, so liquid methane, with, of course, specific composition, specific temperature, and then we add, I don't know if it will start, no. Can we, sorry? No, there is an animation. Could you, on the previous, oh, sorry. Here, okay. Okay, when we put the other cargo, of course, the other methane, then we have such a situations that even in previously, the lower layer is heavier and colder than the upper layer. After a while, because of the pressure of the higher layer, this become more saturated, so warmer and warmer. And there is some moment in which the lower layer is warmer and lighter than the upper layer. And they roll over and release a lot amount of vapor. So this is rollover situations, rollover phenomena. We should avoid such a situations, and to prevent these situations, we should mix or put the other cargo from the nozzle to improve mixing of these two kind of cargo. Okay. Another thing is BOG management, so boil of gas. We have to do something with this, and within transport through the sea, so for the gas carrier, there is quite big problem because daily rate of vaporization is 0.10 to 0.15% of the all amounts. So when we have, for example, 1,000 cubic meters of such a cargo, we will have quite a lot amount of vapor, correct? It will be 1,000 cubic meters, 1,000 or 1 cubic meter? with 100,000? Yeah, so about 1,000 cubic meters, 100, let's say, decimal 10. Okay, so we'll have to do something because during a long voyage, like a few weeks, there is quite a lot amount of vapor, and if we do not make anything with this vapor and keep in the tank, the pressure will increase, the temperature will increase. So we have to remove. By removing, we cooling down the rest of the cargo. And we have actually three methods to keep them at this boiling temperature. So the worst is to release to atmosphere, because when we release to atmosphere, then we have methane as a stronger gas in the atmosphere. We can use it as a propulsion. So all these BOG gases as a vapor should be processed and prepared to be used for engine, for the vessel engine. And it's happened very often, depends on the charter or the agreement between the shipper and owner of the cargo. Or reliquefaction. If there is a facility, we can reliquefy this vapor, but it's also cost. The cost of the fuel and also the cost of the greenhouse emissions, because to reliquefy it, we have to use the traditional fuel. So we increase also the greenhouse gases emission. But anyway, what it's done depends on the agreement between the shipper and owner of the cargo. In case of cisterns, actually we don't have the opportunity to reliquefy. So there is semi-pressure compartment which keep this methane in the pressure between 0 or 1 bar to 20 bars during the warming up, because anyway during transportations with this compartment this gas will become warmer and warmer because the heat from outside will penetrate this tank. So in this case we just have the release valves, safety release valves, which keep the pressure in this tank in the safety ranges. So the conclusions: LPG is odorless, colorless, non-corrosive, no flammable, and non-toxic. So, as was said today, also it's a beauty fuel. It must be understood that the properties which make LPG as a good source of energy, it's also make it hazardous because it's a fuel. And in compared to the traditional fuel, we have also the very cold, extremely low temperature. All available storage and transportation temperature are considered as a cryogenic. It's always less than minus 120 degrees. LPG is renewable source of energy, and we cannot mix, we cannot treat LNG also as a LPG, but LPG can be transported, stored, and transferred with the same infrastructure which is used for LNG. So it's very easy to substitute this LNG, natural gas, liquefied natural gas, with liquefied biogas. It's not flammable. LPG itself cannot be fired, but the vapor can make a flammable mixture. So we should ventilate well the compartment when the gas, the vapors, the low temperature vapors could appear. To large leaks and spills, we have systems safeguards which can prevent and make warnings. Okay, so this is for the first part of this training. Thank you very much. I hope there is no any question. I think things are obvious. Thank you.
Good afternoon, everyone. My name is Marcin Przywarty. I'm representing mainly Maritime University of Szczecin, but today also Klaipėda Science and Technology Park. I have more than 10 years of experience related to the LNG, LBG, mainly because of the projects such as Go LNG or Martech. And today I will focus on the issues related to the safety of the handling, of the transportation of the LBG, and then I will explain. So maybe I will start with the information how we should handle, how we should treat the LBG to secure the safety, and then I will tell you what should be done or how we should behave if the accident happen. And of course, I will also explain what type of accidents can occur. Okay, so let's start with the contribution to the safe operation. Because the crucial part of the activity related to the LBG is transportation. I will focus on the transportation and the LBG, as the LNG can be transported by road, by rail, by inland waterways, and by sea. Of course, because of the volumes, the transportation of the LBG by the big LNG tankers is not very probable, but it is possible. I will also tell you about the regulations, which is about the transportation of the LBG by the sea. Okay, so let's start with the transportation by road, by rail, and by inland waterways. We have three main documents. Which we can where we can find the information about the transportation, about the rules. So for the road, we have the ADR, which is an agreement concerning the international carriage of dangerous goods by road. For the rail, we have the RID, regulations concerning the international carriage of dangerous goods by rail. And for the inland waters, we have ADN. And if we check the content, if we check the scope of those documents, we'll see that they are very similar. Of course, there are differences, but generally there are more or less. Generally, there are very similar. There are almost the same information can be found inside. The ADR consists of 9 parts. It is divided into 2 volumes, but generally we have 9 parts. In the part number 1, we have the general provisions. Part number 2 is a classification. Part number 3 is a list of the dangerous goods. Part number 4 is the packing and tank provisions. Part number 5, consignment procedures. Part number 6, requirements for the construction and testing of packagings and other types of packaging, so tanks and containers and so on. Part number 7 is the provisions concerning the conditions of carriage, loading, unloading, and handling. Part number 8, requirements for the vehicle crews, equipment operation and documentation. Part number 9, requirements concerning the construction and approval of vehicles. And if we compare the ADR with the RID and with the ADN, we'll see that the contents is almost the same. The only difference is that the RID has 2 parts less the last two parts are not included in the RID. So, because the documents are very similar, I'll try to present the general rules together, to not split it into each way of transportation. I will tell about it all together. So, all three documents start with the general safety measures, and here we can find the general rules, not only for the LBG, not only for the LNG, but generally for the transportation of the dangerous goods. So we can find that all participants or parties of the carriage of dangerous goods shall take appropriate measures according to the nature and the extent of the foreseeable dangers so as to avoid damage or injury and, if necessary, to minimize their effects. And they shall, in all events, comply with the requirements. And when the risk occurs, the services, the emergency services, should be notified, and all information should be given to these services. Then we can find the requirements for each party of the transportation. Generally, we have three main participants, three main parties of the transportation. So we have the consignor, carrier, and the consignee. And the consignor should hand over for carriage only goods, only consignments which conform to the requirements of the documents. The carrier who takes over the dangerous goods at the point of departure shall ascertain that the dangerous goods to be carried are authorized for the carriage in accordance with the documents. And the consignee has the obligation not to defer acceptance of the goods without compelling reasons, and to verify after unloading that the requirements has been complied with. Then we can find the more detailed requirements for the other participants of the transportation process. So we can find the requirements for the loader, for the packer, for the filler, for the tank container or portable tank operator, tank wagon operators, and the unloader. But I won't present it in details. The main part of all those three documents is part number 3. So maybe not the main, it is not most important, but if you want to find the information, we should start with the part number 3, where is the list of the dangerous goods. And if we find the proper line, proper entry, we can find the codes. In this list, we do not find all information, but we can find the codes. And here you can see the entries, the lines regarding the LBG. And I will now present the main points which can be found. Of course, there are some differences, but generally the information are the same. So in the first column, we can find the number, and for the LBG, the number is 1972. It's a UN number of the dangerous good. Then we have the name and the description. So the name is a methane, refrigerated liquid, or natural gas refrigerated liquid with high methane content. Then we have the class, and the class code is number 2, which means that it is the gas. Then we have the classification code, which is 3F, which means that it is the refrigerated liquefied gas, and it is flammable. Then we have the packing group, and there is no packing group assigned. Is this here? Yes, we do not have packing group assigned. Then we have the information about the labels which are required, and for the LBG, as for the LNG, the label which is required code, the label code is 2.1, which means this type of label. It is square, a little bit rotated, with the minimum dimension of 10 centimeters, and it should be red. And we can find the class, and as I presented on the previous slide, the class is number 2, and we can have the class symbol, which is the flame for the LBG, and it can be additional text in the middle, but in case of the LBG, there is no additional text. For the rail, for the trains, there is one more label which is required. It is number 13, and it looks like this. It's a triangle, upside down, let's say, with the exclamation mark. The black one and the minimum dimensions are also defined. Additionally, on the carrying the LBG should be marked with the orange-colored plate marking, which gives us the hazard identification number. Sorry. In case of the LBG, it will be 223, and the UN number, and as I said, it is 1972. We have also the minimum dimension defined, and the shape and the size of the numbers. Then we have the code for the special provisions. In this case, it is 392. It's special provisions when we carry the LBG or LNG not as a cargo, but as a fuel for the vehicle, which is fueled by this type of fuel. So it is not very common. Then we have the limited and expected quantities. In case of the LBG, the codes are 0 and E0, which means that it is not permitted to be carried as a limited quantity, and it is not permitted to be carried as an expected quantity. Then we have the requirement for the ADN, so for the inland waterways, we have the additional requirements. There is a carriage permitted, and the code is T, which means carriage is permitted in packages and in tank vessels. And for this carriage, there is a defined equipment which is required, and we have 3 codes. The code is PP, which means the protective that for each member of the crew, the pair of protective goggles, pair of protective gloves, and protective suit and suitable pair of protective shoes should be secured. And on board of tank vessels, protective boots are required in all cases. Then we have the code EX, which means that the gas detector is required, and the code A, which means that the breathing apparatus, ambient air dependent, is also required. Then we have the requirements regarding the ventilation, and for the inland ships, there is an additional requirement that it should be equipped with the blue cone lights, and the number is 1. Then we have the more detailed requirements for the packing, for the tanks, for the bulk containers, for the ADR RID tanks, but I won't go through these codes because it is very detailed information about the pressures, about the sizes, the construction, and so on. Then for the rail and for the road, there is information what type of vehicle can be used, and then the code is FL, which is from the flammable. So the car should be prepared, should be suitable for the carriage of this type of this type of cargo. Then we have the transport category, and the code is 2. Also information about the types of the tunnels through which the LBG can be transported, because it is not possible for each type of tunnels. To be honest, only tunnels of category A only through the tunnels of category A the LBG can be transported. Then we have the special provisions for carriage. And then we have the codes for the loading and unloading and handling. And we have the code CW9, which means that packages shall not be thrown or subject to impact. And there is additional requirement for the roads. Then we have the code CW11, which means that the receptacles should always be placed in the position for which they were designed, and be protected against any possibility of being damaged by other packages. Sorry. And then we have code CW36, which means that packages shall preferably be loaded in open or ventilated wagons, and if it is not possible, the marking the information should be given on the door, warning no ventilation, open with caution. Then for the road we have additional requirement, which code is S2, which means that additional requirements concerning the carriage of the flammable liquids or gases, and there is a list of those requirements, but I won't go very deep to this. Then we have the carriage by sea, but as I said, it is not very probable to transport the LBG cargo by the big ships, but there is a code. The code is called IGC, the International Code of the Construction and Equipment of Ships Carrying Liquefied Gases in Bulk. So we can find the most crucial information about the construction, about the handling of this type of cargo. And I will focus on the chapter number 18, where we can find the operating requirements. The main goal, the most important goal for the IGC code is to ensure that all ships, staff involved in cargo operations have sufficient information about the cargo properties and operating the cargo system so they can conduct cargo operation safely. Those involved in liquefied gas carrier operations shall be made aware of the special requirements associated with and precautions necessary for their safe operation. A copy of the code or the national regulations incorporating the provisions of the code shall be on board every time and every ship covered by the code, and the ship shall be provided with the copies of suitable detailed cargo system operation manuals, and the cargo operation manuals should include the information such as overall operation of the ship from dry dock to dry dock, including procedures for cargo tank cool down and warm up, transfer, including ship-to-ship transfer, cargo sampling, gas freeing, ballasting, tank cleaning, and changing cargoes, cargo temperature and pressure control systems, cargo system limitations, including minimum temperatures, cargo system and inner hull, minimum pressures, transfer rates, filling limits, and sloshing limitations, nitrogen and inert gas systems, firefighting procedures, operation and maintenance of firefighting systems, and use of extinguishing agents. Additionally, the special equipment needed for the safe handling of the particular cargo, fixed and portable gas detection, control, alarm and safety systems, emergency shutdown systems, procedures to change cargo, tank pressure relief valve set pressures, and emergency procedures including cargo tank relief valve isolation, single tank gas freeing, and entry and emergency ship-to-ship transfer operations. The information about cargo, in our case, the information about the LBG should be carried on board, and the content of this information should include a full description of the physical and chemical properties necessary for the safe carriage and containment of the cargo, reactivity with other cargoes that are capable of being carried on board, the actions to be taken in the event of cargo spill or leaks, countermeasures against accidental personal contact, firefighting procedures and firefighting media, special equipment needed for the safe handling of the particular cargo, and emergency procedures. The physical data supplied to the master shall include the information regarding the relative cargo density at various temperatures to enable the calculation of the cargo tank filling limits, and the contingency plans which should be prepared for spillage of cargo carried at ambient temperature shall take into account potential local temperature reductions, such as when the escaped cargo has reduced the atmospheric pressure and the potential effect of this cooling on hull steel. What are the responsibilities? Of course, the person on board who is responsible is always the captain, always master, and the master shall ascertain that the quantity of characteristic of each product to be loaded are within the limits indicated in the International Certificate of Fitness for the carriage of liquefied gases in bulk, and in the loading and stability information booklet, and that the products are listed in the International Certificate of Fitness for carriage of liquefied gases in bulk. Care should be taken to avoid dangerous chemical reactions if cargoes are mixed, and this is particularly important when the tank cleaning procedures are required between the successive cargoes, and when the different cargoes are carried simultaneously at the same time. There are some additional requirements for the cargo at low temperatures. So when carrying cargoes at low temperatures, the cool down procedure laid down for that particular tank piping and ancillary equipment shall be followed closely. Loading shall be carried out in such a manner as to ensure that the design temperature gradients are not exceeded in any cargo tank, piping, and other equipment. If provided, the heating arrangements associated with the cargo containment system shall be operated in such a manner as to ensure that the temperature of the whole structure does not fall below that for which the material is designed. So some general information about the cooling. Generally, the tanks of the LBG tankers are always cooled down. So even if the cargo is unloaded, some portion of the cargo stays just to keep the temperature. There is also information about the trainings for the crew members, and there are, let's say, 2 levels of the trainings. All personnel, so all crew members, shall be adequately trained in use of protective equipment provided on board and have basic training in the procedures appropriate to their duties necessary under emergency conditions. And the officers shall be trained in emergency procedures to deal with the conditions of leakage, spillage, of fire involving the cargo, and a sufficient number of them shall be instructed and trained in essential first aid for the cargoes carried. That's all about the safety of transportation. So to conclude, we have 4 possibilities to transport the cargo. So we can transport LPG by road, by train, so by rails, by inland waterways, and by sea, by ships. And we have the documents, we have the agreements where we can find the information, where we can find the rules for the given type of transportation. Now I will explain, now I will present what we can do or what shall we do in case of the accident. So first I explained what can we do to avoid the accident, but now what we can do if the accident happens. The document where we can find the general information about the procedures is called safety data sheet. It was mentioned by my colleague. The safety data sheet is a document that lists information relating to the occupational safety and health. It should be prepared by the producer of the LPG, and should be provided to each buyer. The safety data sheet must always be available during transport and use and storage. In Europe, the safety data sheets are the part of the system which is called REACH, registration, evaluation, authorization, and restriction of chemicals. The SDS has, because it's a part of this system, it has the constant construction. There are 16 sections, and I will focus on the section number 2, where is a hazard identification, section number 4, first aid measures, and section number 8, exposure controls and personal protection. Here you can see the examples of the SDS prepared by different manufacturers, different producers. So first, the identification of the hazards. I won't dive very deeply into this topic because most of these hazards were presented by my colleagues. So we have the hazards related to the health, because the LPG has a flammable vapors. In high concentrations, it may cause slight dizziness and have an anesthetic effect. In even higher concentrations, because of the reduced amount of the oxygen, reduced consciousness and asphyxiation may result due to oxygen displacement, and long being in these conditions may result in unconsciousness and even death. Of course, because of the low temperature, it may cause severe freezing injuries on skin or on eyes. And for the safety hazards are generally related to the flammable explosive mixture of the LPG. So what we can do to reduce these hazards? To reduce these hazards, we can use the engineering controls. So we can provide adequate ventilation to keep gas and vapor concentration below the flammability limits. Generally, it should be less than 20% of the lower explosive level, so 20% of the 5%. Yes, because the lower explosive level for the LPG is 5%, so it should be lower than 20% of 5%. In confined spaces, local and general ventilation should be provided. We should follow appropriate confined space entry procedures, use the explosion-proof general ventilation and lighting in classified controlled areas, and we should be sure that explosion-proof flashlights and equipment are used. So it was the engineering controls. Of course, we also have to use the PPE, so personal protective equipment, for the eyes and for the face protections. The goggles or the face shields can be used. For the skin and hand protections, the workers, the operators should wear the thermal isolating gloves and clothing when working with the materials that present thermal hazard, hot or cold, in our case cold. We should ensure that the protective equipment is related for the temperature of the material to be handled, and the flame retardant clothing is recommended in any situation where LNG vapors may ignite accidentally. For the respiratory, so breathing protection, self-contained breathing apparatus or equivalent apparatus should be used when we know that there is low concentration of the oxygen, or if the concentration is unknown, and in situations that are immediately dangerous for life or health. If the accident happens, so if we have the contact of the LNG with eye, we should not, it can cause the frostbite. In case of frostbites or freeze burns, we should gently soak the eye with the cool to lukewarm water. We shouldn't wash the eyes with hot water, which is quite obvious. We should try, or we should open the eyelids wide to allow the liquid to evaporate, assuming that it is not a very high volume. So we can imagine that there is one drop of the LNG or the LBG. If the person cannot tolerate light, protect the eyes with the bandage or the handkerchief. Do not introduce ointment into the eyes without medical advice, and we should seek medical attention. If the contact is not with the eye, which is the worst scenario, but if the contact is with the skin, of course it also can cause the frostbite. In case of frostbite or freeze burns, we should remove the containment clothing and flush the affected area with cool to lukewarm water. We should not use the hot water or dry heat. We should seek medical attention, and under no circumstances we should the frozen part be rubbed either before or after the warming. Just to maybe tell a little bit more, it is not like this that if we touch the LBG or if we touch the LNG, we will have the frostbites or frost injuries immediately. Generally, we can put the finger inside and take it away and nothing happens. So it is not like this that it is very, very dangerous, that that the injuries are very probable. So it is possible to put the finger in it and take away. So if we breathe with the atmosphere, as my colleague said, the LBG, the LNG, isn't toxic. So the problem is only that the level of the oxygen is too low. So the problem is caused by not by the LNG, but by the low level of the oxygen, which is caused by the LBG. But LBG or LNG is not toxic. So inhalation of large quantities of LNG vapors may cause central nervous system depression with nausea, headache, dizziness, vomiting, and incoordination. LNG and associated vapor is a simple asphyxiant and may cause a loss of consciousness. serious injury or death by displacing air, thereby resulting in insufficient oxygen to support life. Prompt medical attention is strongly recommended in all cases of inhalation overexposure. Rescued personnel should be equipped with the self-contained breathing apparatus. If we have the victims should be taken to the fresh air quickly. If inhalation victims is not breathing, we should ensure that the airways are open and administer cardiopulmonary resuscitation, so CPR. If necessary, we should have a trained person administer air or oxygen once breathing is restored, and of course we should seek medical treatment. There is one more hazard, one more danger, not very probable, but maybe someone will try. So if we try to swallow the LNG, so if we try to drink it, of course LNG is gas under atmospheric pressure, atmospheric temperature and pressure condition, and ingestion is unlikely, but if it happens, we should seek the medical treatment as fast as it is possible. The last part is the firefighting operation. So in this case, we have the leakage, we have the spill of the LNG or the LBG, and we have the fire. To have a fire, we should have the three conditions. So to make it possible to have a fire, the three components should be secured. We should have the fuel. In this case is LBG, and my colleague presented that the range of the flammability isn't very wide. It is rather narrow, between 5 and 15%. We should have the oxygen, and we should have the ignition source. The ignition source, it can be a spark, it can be an open flame, or it can be the high temperature. And the high temperature is the temperature of the auto-ignition. And because of the different composition, it can be more or less between 550, 600 Celsius degrees. LBG itself is not flammable because of the flammable limits. So in the liquid state, it is not explosive and cannot ignite. To become flammable, it must vaporize and mix with the air, and the range of flammability is between 5 and 15%. Because of the mainly because of the different place of the ignition, we can have, and the different pressures of the LBG, we can have the different types of the fires. So if we have those three parts, those three factors, and we have the fire, we can have the different fire scenarios. The first is the vapor cloud flash fire. The vapor cloud flash fire will occur if we have the late ignition. So ignition will be in the distance from the leakage. Of course, the vapor cloud should be the concentration of the methane in the vapor cloud should be between 5 and 50%, but in some distance from the leakage. In this case, not all cloud will fire immediately at once. The fire can burn forward to the cloud front or backward to the release point, so to the spillage. The speed of propagation, the speed of fire is not very high. It is more or less 10 to 20 meters per second. There is, because of this low speed, the overpressure isn't very high. So the serious consequences are possible only inside of this vapor cloud. Outside, the only problem is the high temperature. So close to this fire, it can be a problem, but it is not an explosion. Yes, it is just the flame. Of course, in the flames we can have serious injuries, but only in the limited space. If the leakage is under pressure, we can have the jet fire. The jet fire occurs if the ignition of the liquid or the vapor of two-phase mixture is in the under pressure condition. Unlikely for the LNG storage tank, because normally it is stored in the atmospheric pressure, so there is no high pressures. But for the tanks, for the LBG, it is possible to transport it with higher pressure, so we can have the jet fire. It may be caused by the vapor leaking from the high pressure sources, so for example pumps, vents, risers, or piping. It can be reason for the severe damages, and but limited to the confined to the local area. Then we have the pool fire. The pool fire is a fire close to the leakage area. Where you have pool, we have the vapors, and the vapors burns close to this pool, just above the pool. Because the leakage, the cloud can move together with wind, so the fire also will tilt in the wind and wraps around the obstacles, such as the front of the dike. In a diked area, fire will remain contained inside. Outside the confined area, fire is free to flow based on the topography, the shape of the area. For spills on the sea, the pool will spread to the steady pool size, and after the ignition, it will shrink. So, to conclude, if we have the spillage, if we have the ignition in a distance, we will have the vapor cloud fire, which can move to the place of the spillage or to the front of the cloud. We can have the jet fire in case that we have the higher pressure. We have the pool fire above the spillage. And of course, the vapor cloud fire can end with the pool fire or the jet fire. So it can transform from one type of the fire to the other one. Okay. Next type of the accident is the vapor cloud explosion. So it is called VCE. It is possible only in the confined areas, in the closed spaces. In this case, the flame speed will accelerate because of the higher concentration to form the deflagration type of explosion. It's not the detonation because the speed of the fire is below the speed of the sound, so it is not as dangerous as the detonation, but still can make a dangerous situation. But it only lasts with congested zone before flames decay to flash fire flame speed. So it is just the explosion for the short time. It is less damaging than the detonation because lower of speed, but can have a large impact, but only to the closed areas. Then we can have the belief. The belief was partly explained by Stefan, and as he said, it is possible for the pressurized flammable liquids exposed to an external fire when the unwetted metal over the vapor space in a container becomes weakened and fail, releasing the liquid that partially flashes to vapor. The flashing vapor expands and ignites as a boiling liquid expanding vapor explosion, so it is called bleed. LNG is not pressurized normally, so there is a very low possibility of bleed, but as I said, LPG can be transported in the cars, in the tanks, in the higher pressure, so it is possible for. The last part, which I want to present because of the shortage of time, is a firefighting plan. So this plan should be prepared in advance. It should be well prepared. What does it mean well prepared? But there's a general information that the firefighting plan should be well prepared. It should avoid the tactics hit and run. In most cases, in fact, the best way how we should behave in the case of the fire is to let it burn. If there is no, if the situation is under control, if there's no danger to the environment, to the people close to the fire, in most cases the best way of handling of the fire is to let it burn. The LNG will burn and nothing more will happen. And of course, we can try to cool down the surroundings. So we can use the water to cool down the surroundings and leave the fire to burn itself. If it is not possible to leave the fire to burn down, we can use the dry powder, and it is the best method of the firefighting, of the best method of the trying to stop the fire. Of course, if it is possible, we can use the fixed installation, but normally there will be the portable extinguishers. In the case of if you want to use the dry powder, we should use all possible dispensers at once. So do not try a little bit, maybe a little bit more, because it is not good. It is not good way of firefighting. So we should use all dispensers at once. The dry powder causes the flame to go out almost at once, but we have to remember that there is no cooling effect. We should avoid to put the direct pressure of the powder jets on the surface of the LNG, because if we do it, we'll increase the rate of the vaporization, so it will be harder to extinguish the fire. Of course, we can use the water, but it is not very easy to extinguish, to stop the fire of the LPG with water. Generally, the water should be used mainly for the cooling down of the surroundings. So we can cool down the surroundings to stop to reduce the damages, but it is not very easy to extinguish the fire with the water. As it was for the dry powder, we should avoid the situation where when we put the water directly to the pool to the leakage of the LPG, again because of the increasing rate of the vaporization. So instead of the extinguish, we'll make the fire bigger. Yeah, and as I said, generally used for the cool down surroundings and essential for the protecting steel work. We can use CO2. CO2 will stop the fire because of the leakage of the oxygen, but it is possible only for the confined, for the closed areas, such as cargo, compressor rooms, electric rooms, inert gas dried room. Some general rules, some general procedure for the firefighting operation. First, we should isolate the source of the leak. If it is possible, stop loading, discharging, and shut down all manifold valves. Of course, sound the alarm. Then provide the protection for equipment and for the firefighters. As it was presented, attack fire with the maximum rate of application of dry powder. Do not agitate to surface of any pool of LNG. Remain on guard against possible reignition. The ignition is possible of the auto-ignition temperature. Even if you stop if we stop the fire, there are still some hot elements. So there is no fire. We stop the action, and then the mixture is between the 5 and 15%, and we have the source and we have the oxygen. The fire can start again. All remedial measures must be situational. So there is no one best way to execute the firefighting operation. First, the firefighter should stop at the safe distance, minimum 100 meters from the accident site. Check the situation, check the size, the location of the gas leak, non-ignited liquids, fire in the gas phase, liquid phase. Check the wind direction and should attack with the wind from behind. Do not use the water on liquid leaks and on fire. Extinguish the fire with the powder if it is available. If possible, shut off escaping gas, liquid, and self-contained breathing apparatus, and full protective clothing should be also used in case of the fire of the LPG. And it was the last point of my presentation. Thank you very much. I'm almost at time.